Hi, this is Jonathan Gardner. We're in section 8.13 of Griffith's Introduction to Electrodynamics, second edition. We're going to talk about sinusoidal waves. This is when you tell a physicist that you have some kind of wave function happening, the first thing to think of is how can I start writing down sinusoidal waves? And so there's only certain kinds of sinusoidal waves that work. Depending on the material you're working in, you have the velocity of the wave, how fast the wave travels. And the general equation for each of the, remember you have a superposition of sinusoidal waves going on. So you can take any number of these and you can add them together. Each of them can have different amplitudes. And basically you can express any function as a sum of these. And what you have is you have your f of x and t that we talked about in the last section is equal to A. A is the amplitude. It's how tall that wave is. So let me just write that down. Amplitude is A. Then you have your cosine, or some people like to use sine. I like cosine. Cosine has a nice property that at zero, where the guts of the cosine is zero, that's your maximum. And then you move off pi degrees in any direction, that's your minimum. Sine starts off at zero and goes up, of course. So the stuff inside the cosine is going to be kappa, k, I guess you can call it k because there's no confusion here. It's not a function, it's actually multiplied by x minus v t. V is the wave function, the wave velocity. So let me just show you this. Where'd my nice little orange red go? So this is the wave number. It's an integer. It goes from 1 to infinity. So you have an infinite number of these guys working against each other. This is the wave velocity. In our string, that was the square root of the tension over the mass per unit length. In our electromagnetic fields, that's the speed of light. And if you're in a vacuum, it's flip back, make sure I get it right. I don't want to tell you something that's wrong. It's the speed of light divided by n, the index of refraction for materials that the wave is propagating through, not in a vacuum. As long as the material is linear, of course. And there's one more part to this. There's the delta. I learned how to write delta today from a Greek. So you actually go like this. That's how you write a delta, backwards. And that delta is the phase shift. Let me just double check I'm using the right words. Is the phase constant. Phase constant. Okay. So one of these waves will look like the picture in the book. So we have our axes here. There's the x, the displacement f here, and this is x. Okay, and at t equals 0, so let's represent that x comma 0. At t equals 0, when everything starts, so you have this maximum here. Okay, the height is a. Okay, the displacement there is delta over kappa, or k. That's this divided by that, and then it's going to go down and then go back up. Okay, and this is one wavelength lambda, where the wavelength lambda is simply 2 pi over the wave number kappa. Okay, let me write that out. It's the wavelength. Okay, and obviously for one of these guys it goes off into infinity. It just keeps going up and down, forever and ever. It's traveling, this is the minus. So the velocity, I think I got it backwards last time. Yeah, so it's traveling this way at velocity v. Each point along here is traveling at velocity v, the wave velocity. Okay, so that makes sense. As time goes on, it basically starts shifting to the right. Okay, t, the period. We talk about the period, capital T, not the tension, the period here. This is equal to 2 pi. The period is how long it takes, if you're sitting at one point along here, how long it takes for you to see a complete cycle. So that's 2 pi over kappa nu, kappa v, the velocity. Okay. This is velocity, not frequency. This is the period. And then you have the frequency nu, which is equal to the inverse of the t, which is just kappa v divided by 2 pi. Okay, and that is the frequency measured in hertz. Oftentimes you'll see omega, the angular frequency, which is just 2 pi nu, which is, let's see, multiply 2 pi nu, you get k. Nu is, you just get kV. It just kills out the kV. Keep your nus and v straight. It's an unfortunate freak of nature. This is the angular. This one will appear in the in complex notation. It's much easier to work with in complex notation than to do trigonometry, which is surprising. You know, you'd think that physicists would be really good at trigonometry, but the truth is as soon as we learn how to use complex notation, we just abandon pretty much there is anything to do with, except for a couple of crutches that'll get you to your complex notation. Anyway, so because it's even, so a cosine function is even. So let's write that down. There's even and odd functions. Even means it's mirrored around the origin. It looks the same on both sides. And odd means that they're anti-mirrored. Basically, it's like if you look in a mirror and you see the opposite of what you see. So cosine is an even function, but sine is an odd function. So you can just as easily take the negative of the guts here, and everything will work out just fine. If you distribute this k, this kappa, well, kappa v is just omega. Where did it go? Right here, kappa v. So you can have kx minus omega t minus delta, or negative kx plus, no, I feel dumb now. They have it wrong here, I think. Yeah, kx minus omega t plus delta could be another way to write this function. Next, we're going to look at complex notation. Thanks for your time. Bye.